We are up to Chapter 8 of Scaling Networks, and so it's Single Area OSPF. Alright, so we're going to look at the operation of OSPF, so we'll look at the features and characteristics, what type of packets it sends, and how OSPF achieves convergence. We'll look at Single Area OSPF in particular, and so we'll look at configuring router IDs and how to configure Single Area OSPF, and we'll look at how OSPF uses cost to determine the best path. And we'll also look at verifying that OSPF is working. We'll also look at OSPF version 3. And so from there, we'll compare the characteristics and operations of version 3, which of course is for IPv6. Very similar, it's just basically just the IPv6 addressing that changes. Okay, so it's characteristics. So OSPF is a link state routing protocol, so we have spoken about that previously. This is a table from we've seen in previous chapters, and so of course version 2 was used for IPv4 and version 3 is used for IPv6. Apart from that, they're as similar as they could be. So basically version 2 and version 3 have been around for a very long time now, but the latest versions have been out since 1998 and 1999 respectively. Okay, so what features does it have? So OSPF uses the Dijkstra algorithm, which is the shortest path first algorithm. And so Dijkstra was a Dutch computer scientist, and he's the one who actually created the algorithm. It wasn't actually meant originally for routing packets. It was more about routing trucks. But anyway, basically RIP and IGRP were the most common ones out there, and well, they certainly had their flaws, and so someone decided, well, I did the Dijkstra algorithm back in uni. Let's try and make that happen for data routing. And so from there, they've done it, and so of course, each routing protocol has its own different administrative distance to basically decide which one is better. And so Cisco has said that OSPF has an administrative distance of 110, which makes it less reliable than IGRP and EIGRP. Don't necessarily agree with that, but I suppose you can modify it yourself. Yeah, so I think they've done it based entirely on metric and nothing else. But anyway, now OSPF is classless, so again it sends masks with network addresses, so it makes it a little bit better, quite efficient, converges quickly, it's scalable, and it's secure. Okay, so what components does it have? So basically it does different things for different reasons. So it actually creates an adjacency table or neighbor table, and so basically what it does is it keeps track of its neighbor routers. And so if it loses adjacency, so they use hello packets to keep track of one another. If after a timeout they stop receiving hello packets, they will actually deem that other router to be down, and they will start recalculating their routes to destinations. There is a link state database, of course, so that's basically where it keeps a track of every network that it's been told about, and also what routers connect into each network and things like that. And so from there it has complete information on the entire network that's been advertised in OSPF. So every router will actually end up with the same database as each other. Of course, their routing tables will look different because each router is in a different position in the network, but they actually start with the same information. And so basically, once they've got a complete link state database, they will then run the shortest path first algorithm through that database to then figure out which is the best route to every destination, and then it will then fill in entries in the routing table, of course, so that you then can forward packets. So to get all of these jobs done, it has several types of packets, and so there's hello packets, there's database description, there's link state requests, link state updates, and link state acknowledgements as well. Now, so how does OSPF operate? So the first thing it does is when a router boots up, it's configured and it's starting up OSPF. It will start advertising its existence by sending hello packets, and so every router will send hello packets. So it's every 10 seconds by default over most links. And so, of course, once you've seen a hello packet from a neighbor, that's when you actually start exchanging information. You make sure that you can form adjacency and go from there. And so once they've formed adjacency, they will then do link state advertisements to flood the area with their information from the databases, to fill up their databases. And then once their database is full, they will then run the SPF algorithm and then figure out the best routes to every destination. And then, of course, once that's been done, it will then fill the routing table with all the routes. So, as we've implied, there's single area OSPF and multi-area OSPF. Now, single area OSPF is very much like how all other routing protocols were done up until now, so RIP and EIGRP. And so all routers are all communicating with one another. Now, multi-area OSPF is designed for much larger networks, and so you actually organize things in a hierarchical way. Area 0 has a special purpose in multi-area OSPF. It's deemed to be the backbone or the core of the network. And then every other area needs to connect to Area 0. And so basically the areas are defined on a per interface basis. And so, of course, all of the interfaces on all of these routers are all in Area 1. Of course, router 1 here actually has at least one interface in Area 1 and at least one interface in Area 0. So that makes it a border router. It's a border between the areas. Same with router 2, but it's of course between Area 0 and Area 51. And so the beauty of this is there's actually a separate database for every area. And so as networks get bigger, again, much the same as static routes, the number of calculations required would actually grow exponentially, and also the amount of traffic that would need to move around the network would grow exponentially. And so by separating the network into areas, you can sort of keep the databases smaller, and there'll be a lot less sort of traffic used to get that working. And so Area 1 will actually send a summary of its networks to Area 0, and that's all the other area routers will get, is just a summary of the different areas. Router 1, of course, will have direct information on both, but it is also the border router, so that's how the summary information goes between areas. And so if you've got a network that's being unreliable, on a large network, that would be a problem, where if it's cycling, going up and down fairly regularly, that would create a major amount of traffic. But with multiple areas, it would only affect the area that it's in. So that's, again, another advantage of it. So how do we encapsulate OSPF messages? So OSPF has its own layer 3 header after the IP layer 3 header, and so the header consists of OSPF multicast address, which is 224.0.0.5 or 0.0.6, depending on the router's function in the network. The OSPF packet header identifies the type of OSPF packet, the router ID and the area ID, and the packet type contains the specific packet type information. And so the packet types are hellos, database descriptions, and so basically what we spoke about a couple of slides ago. Now, if you remember, RIP version 1 broadcast its updates. RIP version 2 does a multicast, and so OSPF does multicast as well, as does EIGRP. And so you have your bundling header, your IP header, and then has its own OSPF packet header, which one of the fields, of course, is type, and then, of course, you actually have that specific packet itself for whatever information is being moved. Now, packet types, you have hello, database description, link state request, link state update, and link state acknowledgement. And so basically hello is, of course, how the routers keep track of one another to maintain their adjacency. Database description is just sent around every now and then. It's basically the version number again. So, you know, this is the latest version of the database. And so if everyone's got the same number, it's all good and it's great. If this database description arrives to a router that has an older version of the database, that's when you'd actually send out a link state request. And so from there, of course, the response to that is a link state update. I ask for something, you get the update. And then from there, of course, there's an acknowledgement saying that, hey, yes, that packet did arrive. Now, hello packets are used to discover neighbours, establish neighbour adjacencies, advertise parameters both routers must agree upon in order to become neighbours, and elect designator and backup designated routers. So we'll talk about that, I think, in the next chapter or two. And so designated router and backup designated routers are only done on multi-access networks. And so basically, as we saw, type 1 is hello, and so on and so on. So the hello interval is how often a router sends hello packets. That information is sent in a hello packet, and both routers need to be set up with the same hello interval. If they're different, they won't form adjacency. Router priority is basically about that DR BDR election, so that doesn't have to match, because you know the whole point of it is that you have different routers with different priorities. The dead interval again is how long a router waits to hear from a neighbour router before declaring the router out of service, and so that's basically how long since the hello packets have arrived that will start thinking that the router is dead. And so DR BDR field contains the ID for the DR and BDR routers, and then a list of neighbours is the router ID for all adjacent neighbouring routers. And so that's all just sort of update information so they can keep track of one another. So hello and dead intervals must be the same interval setting on neighbouring routers, and so you transmit it to 224.0.0.5. Of course, that's a multicast address, and FF02 of course is multicast as well, and it's address number 5 again, so it's consistent. Sent every 10 seconds by default on multi-access networks, every 30 seconds on non-broadcast type networks like frame relay. Dead intervals are by default 4 times hello interval, so 10 seconds for a hello packet, so 40 seconds for the dead interval. If the dead interval expires before the router receives a hello packet, the OSPF removes the neighbour from its link state database. The router then floods the LSDB with info about that down neighbour. So link state updates. They contain one or more link state advertisements. So the update is the packet. Advertisements are quite possibly multiple entries within that packet. Routers initially send type 2 DBD packets in abbreviated list of the routers database, basically, and receiving routers check against their own link state database. A type 3 link state request is used to by the receiving router to request more information about an entry in the database description, and then type 4 update is then sent to reply to that, as in you ask for, you request information, the update is the information. Now, OSPF operational states, and so this is actually about neighbour adjacencies, it's not about the entire OSPF system. And so basically, as neighbours negotiate with one another, they go from the down state to full adjacency state, basically. Now, down means no packets have been received, but it may well have sent its own hello packets. And it means hello packets have been received that contain the sending router's ID. 2A means that there have been hello packets in 2 directions. Now, the reason there's a border there is when you have a multi-access network and you have DRs and BDRs, 2 state is an important state that actually some routers will stay on. But if you have a network type that does not have, is non-multi-access, It will actually go beyond that for all routers. And so you've got exchange start, exchange, and then loading state, and then full state. So basically, exchange start is you negotiate a master-slave relationship in the database description packets. And then from there, you have exchange, where they exchange those DBD packets. And then, of course, they'll do LSRs and LSUs to do it. And then from there, loading is where you get all your information, you put it all together, and you fill up your database, basically. And so, and full adjacency means they have converged databases. Without a establishing neighbor adjacencies. And so without a pre-configured router ID or loopback address, R1 has a router ID of 172.16.5.1 and R2 has a router ID of 172.16.5.2. So basically, when OSPF starts, the first thing it wants to do is it wants to identify itself, and so it wants an ID. And so it can either be, you can type in a router ID command, or you can have a loopback address. They're the preferred ones just because they're software states, they're not dependent on a hardware status. But the last point, the last item is basically a physical interface. Of course, that physical interface needs to be up. And so once it's identified itself, and so it will actually use the highest IP address on a physical interface if that's the way it goes. And so that basically you send your hello packet saying, hey, my router ID is this. Is there anyone else out there? Basically, that's what the conversation is saying. And then the other router will reply back saying, hey, hi, I'm router ID such and such, and here is my neighbor list. And then the two routers have exchanged information, so they're in the two-way state. And so, of course, router 1 will then send us neighbor list as well. And if you're on a multi-access network, then a DR-BDR election will happen. And so basically the one with the higher IP address, in this case, R2 is one higher, and so that will end up being designated router, and R1 will end up being backup designated router. But we will go into more depth in that in a later chapter. Okay, so why have a DR-BDR election? And so if you have all of these routers connected into an Ethernet network, for example, as you add a router, again, the number of adjacencies will grow exponentially. And so that's, you know, that does sort of take more information. Also, if there's a change in the network, suddenly there will be link state updates flooding everywhere because everyone will talk to everyone as soon as they find that information out. And so it makes things very inefficient. And so basically you have, so basically if you have a DR and a BDR, let's just say it's the top two here, then all the other routers, all routers will form a full adjacency with the DR and BDR, but they actually only go to that two-way state for the, was it two-way state? Yeah, two-way. Between each other, but they have a full adjacency with the DR and BDR. And so then, if one of the routers notices a change, it will tell the DR, and then the DR will tell everyone else. And so it's sort of one there, and then the DR will talk to that one, and that one. And so it makes it a lot more efficient. So that's why we bother. So synchronizing OSPF databases. After the two-way state, routers need to synchronize their databases and use the other four types of packets to exchange information. And so you've got the exchange start state, and so basically the router with a higher ID will end up being the master between them, you know, the master-slave setup. And so from there, then you go exchange state. Here's my LSDB, thanks to the info. Here's my LSDB, thanks to the info. And so they just exchange information. about their databases, and then if there are networks in the description that the others don't know about, that's when they actually send a link state request saying, hey, I need information about this, and they'll send it back and vice versa. Okay, single area OSPF version 2. Now we're going to use this topology in the slides here, and so we've got 3 routers connected in a loop, and each router has a LAN hanging off of it, and router 2 has a connection to the internet. So how do we configure it? So router OSPF. Now we actually have to not just type in router OSPF, we need to type in a process ID as well. So we've already done EIGRP, and we've seen autonomous system numbers. They had to match amongst all the routers for them to become adjacent. Well, this number does not have to match. It's just a process number. It's just a way to uniquely identify an instance of OSPF. Now, so it's only of local significance, it's not shared. And so many people just use one. But anyway, so once you're in, of course, you go into router config mode, and then what options are available? So the old question mark. And so there's auto cost. And so we'll talk about that a bit later. So it's a way of modifying how the cost is calculated. Network commands, as you've done previously as well. They are slightly different with OSPF. We'll cover that as well. Of course, there's no. Passive interface works the same. There's priority. There's router ID command, which of course we have done in EIGRP as well. And there's also default information originate, things like that as well. Okay, so router IDs are used to uniquely identify an OSPF router. Router IDs are 32 bits long, like an IP address, in both version 2 and version 3. So you actually need to use an IPv4 address as a router ID for, even though it's IPv6. They are used in the election of a DR if a priority number is not configured. So you can actually set a priority, and it's on a per interface basis, and that is the preferred way of deciding who is going to be DR and BDR. But the default number is 1. And so if you haven't done that yet, 1 is going to be the default, and so that'll be a tie, and so router ID is used as a tiebreaker. Hopefully you don't have more than one router with the same router ID. So you can do router ID and number within router config mode, and that will set its router ID. If you haven't done that, it will then look for a loopback interface. And so again, loopback interfaces are a virtual thing, and so again, more reliable. Router ID, if you've gone to the trouble, we're going to use it. If not, we'll use the highest IP address number of any loopback interfaces you've got. If you don't have one of those, that's when we start looking at a physical interface, as I said before. It's not recommended because if you have a router ID and that interface then dies, yeah, the router ID selection process has to start over, and it's just not great. If you have a loopback address used, do not route this network using a network statement. Okay, so some example commands. So we're using router OSPF 10, set a router ID of 11111. It is router 1, sort of makes sense. And bang, we've got it done. But we don't have network commands yet, but anyway. But you can do show IP protocols to see that the router ID has taken, basically. Now, if you've changed the router ID, but OSPF is already running, you'll actually have to clear IP OSPF process. So basically it closes OSPF, starts it again, and it'll come back with that router ID. Okay, now using a loopback interface as a router ID, older iOS versions did not have the router ID command, and so it used to use a loopback. Now, so you can just create interface loopback 0, give it an IP address of all the ones, and a 32-bit mask is, a host address basically. So you wouldn't advertise it as a network. And so how do we enable OSPF on interfaces? And so again, you go router OSPF 10 was the example, and then you do network and the network name. Now, when we did EIGRP, it did mention the use of wildcard masks, but it was optional. With OSPF, it is required. And so you do Wildcard Mask, then area, and then area ID. Because remember, we were talking about multi-area OSPF. If you're doing single area OSPF, you put everything in area 0. But of course, this gives us the ability to actually create multiple areas. So that is required. You can't shortcut the network command in OSPF. You have to do the full thing. So network number, wildcard mask, area, and then the number. So area 0 you'd often put. So in this case, router 2 has 3 interfaces in area 0, so 3 network statements are used, not 6 network statements for all 6 networks in the entire area. Yeah, so much the same again. You only have to do network statements for the directly connected networks on a router. Okay, so wildcard mask. To determine the wildcard mask, you can subtract the normal mask from 255, or 32 ones. And so that's often an easy way to do it. And so a wildcard mask, of course, coming back to access control list, what we did in CCNA 2, basically if it's a 0, you need to match that bit. With a 1, it's ignore that bit. And so if you've got a 24-bit mask, which is what we're talking about here, it ends up being the opposite, so 000255. So we care about the first 3 octets, we don't care about the last. And so, of course, different subnet masks will end up with a different wildcard mask. Now you can again summarize these things with the wildcard mask as well, depending on your setup. And that can do more than one interface or network at the same time if they're all sort of subnets of one another. But that does depend on your design. Okay, so you can advertise a particular network calculating the wildcard mask, or you can advertise the IP address. And so if you set 172.16.1.1 on an interface, you can actually do 172.16.1.1, 32 zeros, which means match that. And so basically, wherever you find that IP address, that is involved in area 0. So away you roll. So these are examples of those. And so you could have actually gotten keen and go on 172.16.0.0, 0.0.255.255, and it would have done both of those networks at the same time. But it's up to you. You've got to do it the way you understand it. So passive interface is again much the same as what you've seen previously with other routing protocols. An interface configured as passive interface does not send OSPF messages. Best practice for interfaces that have users attached for security purposes, as well as it doesn't waste bandwidth. Okay, so passive interface and then the name of the interface. And so if you do show IP protocols, it tells you what passive interfaces have been set, which is good for you to do some fault finding if things aren't working well. Now the OSPF metric. Now OSPF was designed back when fast Ethernet was the fastest thing out there. And so that was what they used as a reference bandwidth, 100 million. So basically anything 100 megabits or faster ends up having the same metric. Now 100 megabits and 10 gig Ethernet, they are very different. And so they shouldn't come up with the same cost. That would make them all of equal interest, and that's just not right. And so if you have interfaces faster than 100 megabits, you should be playing around with the auto, with the bandwidth reference number, basically. So of course, the lowest cost is best path, but yeah, 1's as low as it gets. So OSPF accumulates costs. The cost for a destination network is an accumulation of all the cost values from source to destination. So the cost to reach R2 from LAN 1 is 65, because you've got 1 there, you've got 1 there, and you've got 64 there. So that's what the cost is. And so as you can see, 110 is the admin distance, 65 is the metric. Changing the OSPF reference bandwidth affects only the OSPF calculation used to determine the metric, not the bandwidth on the interface. The auto cost reference bandwidth command to change OSPF reference is, and so of course the default is 100 megabits per second. You might want to speed that up. And so there's an example coming. So if you use 10,000, it'll end up being just gigabit and 10 gig being equal as opposed to that. Of course, if you use, that was 1,000. If you use 10,000, you'll actually end up with, of course, that's megabits. You'll end up with a sensible spread of costs. So, of course, it will up the cost for your slower links, but that's pretty sensible as well. If the routers in the topology adjusted to accommodate gigabit links, the cost of the serial link is now 647 as instead of 64. The total cost from R1 to R2 is now 648 instead of 65. If there were fast Ethernet links in the topology, OSPF would make better choices. So that's all about having a meaningful metric. So of course, again with the serial links, much the same as EIGRP, serial links, it will always assume 1.544 megabits per second, and so you should do the bandwidth command to actually fix that. And so if you look at show interfaces, bandwidth 1544, and so that's, if that's what the link really is running at, great. If it's not, you should change the bandwidth and then change the metric. So bandwidth 64 means that this link is running at 64 kilobits a second, and so away you roll. And so that will actually then recalculate the cost, and it'll make better routing decisions. Command only modifies OSPF bandwidth metric, does not modify the actual link bandwidth. You can, instead of doing the bandwidth command, you can actually do IP OSPF cost. And that will work perfectly well. I personally rather not do that. A router's a computer. It can do math very well. So I just do the bandwidth 64 or whatever it might be and let it calculate it. And so away you roll. But it's really up to you, or it might be the organisation you work for, they might have rules. Okay, so you can do show IP OSPF neighbour to verify the router has formed an adjacency directly with connected routers. It's one of the tools I use regularly for fault finding. So you can, this is router 1 and it has adjacency, I'm assuming, with router 3 and router 2, hence their router IDs. Priority is just for DR BDR, which is irrelevant on serial links. State full, which means I've gone through the full process of exchanging routes, and so that's very good. Dead time, basically in 37 seconds, if I don't hear a hello packet from our neighbour, we're going to declare it dead. Now, of course, would be a 40-second delay, so it's 3 seconds since we've heard from router 3, and it's 10 seconds from router 2, so I'm assuming that's going to have a hello packet arriving any time now. And so it shows you the address of the interface that it's been communicating with, and so 192.168.10.6 is here, 192.168.10.6, and so that's the interface that was speaking to router 1. And then there's the local interface that you use to talk to it. Okay, so show IP protocols gives you again the summary of the routing protocol, and so it's OSPF 10, so that's the process number. Router ID is all the ones. Routing for networks, and so they're the network commands that have been put into there, and these are the adjacent routers that have exchanged information. And of course the admin distance is 110. You can do show IP OSPF. That gives a lot of information. Got to admit, I don't do it all that often, but anyway. Show IP OSPF interface. You can just get a one-line summary of each interface. with brief, sorry. Okay, so single area OSPF version 3. So version 3, of course, is used for IPv6. When it comes to what information it does, it's damn near identical. It's just that the addressing is for IPv6 as opposed to IPv4. So, comparing the two, they're both link state. They use sort of shortest path first. They use the same metric. Two-level hierarchy is the same. Packet types are the same. Neighbor discovery is the same. DRBDR function is the same, and it even uses the same router ID process. Differences, and so of course version 3 does IPv6. It uses IPv6 of course for source and destination addresses, of course unicast for or link local addresses instead of a unicast, but of course it uses IPv6 multicast addresses. Now, you don't do network commands with IPv6, but that's consistent with other protocols as well. You do IP OSPF processor the area such and such in the interface itself. You actually have to turn on IPv6 unicast routing. We've covered that previously as well. And when it comes to authentication, it actually is encrypted, so it uses IPsec as opposed to plain or MD5. Now, link local addresses. IPv6 link local addresses enable a device to communicate with other IPv6 enabled devices on the same link and only on that link. So there's no inter-network communications with link local addresses, hence link local. Packets with a source or destination link local address cannot be routed beyond the link where the packet is originated. Link local addresses are used to exchange OSPF version 3 messages. And so, of course, be sure to turn on IPv6 routing and assign IPv6 addresses to the interfaces before enabling OSPF version 3. And so, of course, you need to give them IPv6 addresses. And of course, you can personalize the link local addresses as well to make them a little more brief and user-friendly. So how do we do it? So you have to turn on IPv6 unicast routing. You configure your link local addresses if you wish to. Configure a router ID. Configure routing specifics such as a reference bandwidth. Again, bandwidth commands on serial links is a good idea, and then you actually enable it with IPv6 OSPF area commands, and that's on the interfaces. So how do we verify it? Show IP interface brief. Now, of course, these are the link local addresses that are automatically generated using EUI64. I'm saying it's good for a computer to do that, not as friendly for us. Of course, you can manually do it yourself. On router 1, you can make all of the interfaces FE80::1. On router 2, you can of course do ::2, etc., etc. Makes it a lot easier, and also static routes and things like that makes it much easier. So you can do IPv6 router OSPF process ID global command to enter config mode. You do a router ID. You don't have to do much else. You might want to do the auto cost reference bandwidth command, but that's probably about it. So, if you've changed the router ID, of course, you need to clear the IPv6 OSPF process command to reset the router ID to be what you want. And so then you go into the interfaces. Now, IPv6 OSPF 10, so that's the process ID, and then you say what area it belongs to. Because we don't do network commands, you have to do it on a per interface basis. But it's the same command, makes it a little bit easier. Again, you can do show IPv6 OSPF neighbor, and so router IDs, full adjacency, and so that all looks very happy. Show IPv6 protocols. Now, it doesn't actually tell you what networks are involved because you do it on a per interface basis, and so it actually just lists the interfaces that are members of each area. And show IP OSPF interface brief. It gives you a line-by-line summary of the OSPF settings. Show IPv6 route. So of course you're going to have a source of O for the OSPF routing protocol. And as you can see, next hops are actually the link local address. There's the end of the chapter. So we've looked at how OSPF operates, and we've looked at implementing single area OSPF for version 2 and version 3 of OSPF. And so, of course, there is a demo to come, and that will show you how to do the configuration. Have a nice day.